vastly more powerful and network can start being used for increasingly diverse purposes, and remarkably, relational databases turn out to generalize very well beyond their original scope of business data processing to a broad variety of use cases. Much of what you see on the web today is still powered by relational databases, be it online publishing, discussion, social networking, e-commerce, games, software as a service, productivity applications, or much more. The birth of NoSQL. Now, in the 2010s, NoSQL is the latest attempt to overthrow the traditional model of dominance. The name NoSQL is unfortunate since it doesn't actually refer to any particular technology. It was originally intended simply as a catchy Twitter hashtag for a meetup on open source distributed non-relational databases in 2009. Nevertheless, the term struck a nerve and quickly spread through the web startup community and beyond. A number of interesting database systems are now associated with the NoSQL hashtag, and it has been retroactively reinterpreted as not only SQL. There are several driving forces behind the adoption of NoSQL databases, including a need for greater scalability than relational databases can easily achieve, including very large datasets or very high write throughput. A widespread preference for free and open source software over commercial database products, specialized query operations that are not well supported by the relational model, frustration with the restrictiveness of relational schemas, and a desire for a more dynamic and expressive data model. Different applications have different requirements, and the best choice of technology for one will be different from the best choice for another use case. It therefore seems likely that in the foreseeable future, relational database will continue to be used alongside a broad variety of non-relational data stores, an idea that is sometimes called polyglot persistence. The object relational mismatch. Most application development today is done in object-oriented programming languages, which leads to a common criticism of the SQL data model. If the data is stored in relational tables, an awkward translation layer is required between the objects in the application code and the database model of tables, rows, and columns. The disconnect between the models is sometimes called an impedance mismatch. Object Relational Mapping (ORM) frameworks like Record and Hibernate reduce the amount of boilerplate code required for translation layer, but they can completely hide the differences between the two models. For example, Figure 2.1 illustrates how a resume, a LinkedIn profile, could be expressed in a relational schema. The profile as a whole can be identified by a unique identifier, user underscore ID. Fields like first underscore name and last underscore name appear exactly once per user, so they can be modeled as columns of the user table. However, most people have had more than one job in their career positions. People may have varying numbers of periods of education and any number of pieces of contact information. There is one-to-many relationship from the user to these items, which can be represented in various ways. In the traditional SQL model, SQL, prior to SQL 1999, the most common normalized representation is to put positions, education, and contact information in separate tables, with a foreign key reference to the user's table, as in Figure 2.1. Later versions of the SQL standard added support for structured data types and XML data. This allowed multi-value data to be stored within a single row, with support for querying and indexing inside those documents. These features are supported to varying degrees by Oracle, IBM databases including IBM DB2, MySQL, and PostgreSQL.
A third option is to encode jobs, education, and contact info as a JSON or XML document. Store Store it on a text column in the database and let the application interpret its structure and content. In this setup, you typically cannot use the database to query for values inside that encoded column. Figure 2.1 representing a LinkedIn profile using a relational schema. Photo of Bill Gates courtesy of Wikimedia Commons. Ricardo Stockert, Agência Brazil. For a data structure like a resume, which is mostly a self-contained document, a JSON representation can be quite appropriate. See example 2.1. JSON has the appeal of being much simpler than XML. Document-oriented database like MongoDB, RethinkDB, CouchDB, and Espresso support this data model. Example 2.1 representing a LinkedIn profile as a JSON document. Some developers feel that the JSON model reduces the impedance mismatch between the application code and the storage layer. However, as we shall see in Chapter 4, there are also problems with JSON as a data encoding format. The lack of a schema is often cited as an advantage. We will discuss this in schema flexibility in the document model. The JSON representation has better locality than the multi-table schema in Figure 2.1. If you want to fetch a profile in the relational example, you need to either perform multiple queries, query each table by user underscore ID, or perform a messy multi-way join between the user's table and its subordinate tables. In the JSON representation, all the relevant information is in one place, and one query is sufficient. The one-to-many relationships from the user profile to the user's position, educational history, and contact information imply a tree structure in the data, and the JSON representation makes the tree structure explicit. Figure 2.2, one-to-many relationships forming a tree structure. Many-to-one and many-to-many relationships. In example 2.1 in the preceding section, region underscore ID and industry underscore ID are givens as IDs, not as a plain text strings. Greater shuttle area and philanthropy. Why? If the user interface has free text fields for entering the region and the industry, it makes sense to store them as a plain text strings. But there are advantages to having standardized list of geographic regions and industries and letting users choose from a drop-down list or autocompleter. Consistent style and spelling across profiles, avoiding ambiguity, i.e. if there are several cities with the same name. Ease of updating, the name is stored in only one place, so it is easy to update across the board if it ever needs to be changed, i.e. change of a city name due to political events. Localization support, when the site is translated into other languages, the standardized list can be localized, so the region and the industry can be displayed in the viewer's language. Better search, i.e. a search for philanthropist in the state of Washington can match this profile because the list of regions can encode the fact that the shuttle is in Washington, which is not apparent from string greater shuttle area. Whether you store an ID or a text string is a question of duplication. When you use an ID, the information that is meaningful to humans, such as the word philanthropy, is stored in only one place, and everything that refers to it uses an ID. which only has meaning within the database. When you store the text directly, you are duplicating the human meaningful information in every r- record that uses it. The advantage of using an ID is that because it has no meaning to humans, it never needs to change. The ID can remain the same even if the information it identifies changes. Anything that is meaningful to humans may need to change sometime in the future, and if that information is duplicated, all the redundant copies need to be updated. That incurs write overheads and risk consistencies where some copies of the information are updated but others aren't. Removing such duplication is the key behind normalization in databases. Note: database administrators and developers love to argue about normalization and denormalization, but we will suspend judgment for now. In part 3 of this book, we will return to this topic and explore systematic ways of dealing with caching, denormalization, and derived data. Unfortunately, normalizing this data requires many to one relationships. Many people live in one particular region and many people work in one particular industry, which don't fit nicely into the document model. In the relational databases, it's normal to refer to rows in other tables by ID because joins are easy. In document databases, joins are not needed for one-to-many tree structures, and support for joins is often weak. If the database itself does not support joins, you have to emulate a join in application code by making multiple queries to the database. In this case, the list of regions and industries are probably small and slow changing enough that the application can simply keep them in memory. But nevertheless, the work of making the join is shifted from the database to the application code. Moreover, even if the initial version of an application fits well in a join-free document model, data has a tendency of becoming more interconnected as features are added to applications. For example, consider some changes we could make to the resume example. Organizations and school as entities. In the previous description, organization, the company where the user worked, and school underscore name, where they studied, are just strings. Perhaps they should be referenced to entities instead. Then each organization, school, or university could have its own web page with logo, newsfeed, etc. Each resume could link to the organizations and school that it mentions and include their logos and other information. See figure 2.3 for an example from LinkedIn. Recommendations. Say you want to add a new feature. One user can write a recommendation for another user. The recommendation is shown on the resume of the user who was recommended, together with the name and photo of the user making the recommendation. If the recommender updates their photo, any recommendations they have written need to reflect the new photo. Therefore, the recommendation should have a reference to the author's profile. Figure 2.3. The company name is not just a string, but a link to a company entity. Screenshot of linkedin.com. Figure 2.4 illustrates how these new features require many-to-many relationships. The data within each dotted rectangle can be grouped into one document, but the references to organizations, schools, and other users need to be represented as references and requires joins when queried. Figure 2.4 extending resumes with many-to-many relationships. Are document database repeating history? While many-to-many relationships and joins are routinely used in relational databases, document databases and NoSQL reopen the debate on how to best represent such relationships in a database. This debate is much older than NoSQL. In fact, it goes back to very earliest computerized database systems. The most popular database for business data processing in the 1970s was IBM's Information Management System, IMS, originally developed for stock keeping in the Apollo space program and first commercially released in 1968. It is still in use and maintained today, running on OS/390 on IBM mainframes. The design of IMS used a fairly simple data model called the hierarchical model, which has some remarkable similarities to the JSON model used by document databases. It represented all data as a tree of records nested within records, much like the JSON structure of Figure 2.2. Like document databases, IMS work well for one-to-many relationships, but it made many-to-many relationships difficult, and it didn't support joins. Developers had to decide whether to duplicate denormalized data or to manually resolve references from one record to another. These problems of the 1960s and 70s were very much like the problems that developers are running into with document databases today. Various solutions were proposed to solve the limitations of the hierarchical model. The two most prominent were the relational model, which became SQL and took over the world, and the network model, which initially had a large following but eventually faded into obscurity. The great debate between these two camps lasted for much of the 1970s. Since the problem that the two models were solving is so relevant today, it's worth briefly revisiting this debate in today's slide. The network model. The network model was standardized by a committee called the Conference on Data Systems Languages, CODASIL, and implemented by several different database vendors. It is also known as the CODASIL model. The CODASIL model was a generalization of the hierarchical model. In the tree structure of the hierarchical model, every record has exactly one parent. In the network model, a record could have multiple parents. For example, there could be one record for the greater Shuttle Area region, and every user who lived in that region could be linked to it. This allowed many to many and many to one and many to many relationships to be modeled. The links between records in the network model were not foreign keys, but more like pointers in a programming language, while still being stored on disk. The only way of accessing a record was to follow a path from a root record along these chains of links. This was called an access path. In the simplest case, an access path could be like the traversal of a linked list. Start at the head of the list and look at one record at a time until you find the one you want. But in a real world of many-to-many relationships, several different paths can lead to the same record, and the programmers working with the network model had to keep track of these different access paths in their head. A query in CODASIL was performed by moving a cursor through the database by iterating over list of records and following access paths. If a record had multiple parents, i.e. multiple incoming pointers from other records, the application code had to keep track of all the various relationships. Even CODASIL committee members admitted that this was like navigating around an n-dimensional data space. Although manual access path selection was able to make the most efficient use of their very limited hardware capabilities in the 1970s, such as tape drives, whose seeks are extremely slow, the problem was that they made the code for querying and updating the database complicated and inflexible. With both the hierarchical and the network model, if you didn't have a path to the data you wanted, you were in a difficult situation. You could change the access paths, but then you had to go through a lot of unwritten database query code and rewrite it to handle the new access paths. It was difficult to make changes to an application's data model. The relational model. What the relational model did, by contrast, was to lay out all the data in the open. A relation table is simply a collection of tuples, rows, and that's it. There are no labyrinthine nested structures, no complicated access paths to follow if you want to look at the data. You can read any or all of the rows in a table, selecting those that match an arbitrary condition, You can read a particular row by designating some columns as a key and matching on those. You can insert a new row into any table without worrying about foreign key relationships to and from other tables. In a relational database, the query optimizer automatically decides which part of the query to execute in which order and which indexes to use. Those choices are effectively the access paths, but the big difference is that they are made automatically by the query optimizer, not by the application developer. So we rarely need to think about them. If you want to query your data in new ways, you can just declare a new index and queries will automatically use whichever indexes are most appropriate. You don't need to change your queries to take advantage of a new index. See also query languages for data. The relational model thus made it much easier to add new features to applications. Query optimizers for relational databases are complicated beasts, and they have consumed many years of research and development effort. But a key insight of the relational model was this: you only need to build a query optimizer once, and then all applications that use the database can benefit from it. If you don't have a query optimizer, it's easier to hand code the access paths for a particular query than to write a general purpose optimizer. But the general purpose solution wins in the long run. Comparison to document databases. Document databases reverted back to the hierarchical model in one aspect, storing nested records, one-to-many relationships like positions, education, and contact underscore info in figure 2.1 within their parent record rather than in a separate table. However, when it comes to representing many-to-one and many-to-many relationships, relational and document databases are not fundamentally different. In both cases, the related item is referenced by a unique identifier, which is called a foreign key in the relational model and a document reference in the document model. That identifier is resolved at read time by using a join or follow-up queries. To date, document databases have not followed the path of Codacil. Relational versus document databases today. There are many differences to consider when comparing relational databases to document databases, including their fault tolerance properties, see Chapter 5, and handling of concurrency, see Chapter 7. In this chapter, we will concentrate only on the differences in the data model. The main arguments in favor of the document data model are schema flexibility, better performance due to locality, and that for some application it is closer to the data structure used by the application. The relational model counters by providing better support for joins and many to one and many to many relationships. Which data model leads to a simpler application code? If the data in your application has a document-like structure, i.e. a tree of one-to-many relationships where typically the entire tree is loaded at once, then it's probably a good idea to use a document model. The relational technique of shredding, splitting a document-like structure into multiple tables like positions, education, and contact underscore info in figure 2.1 can lead to cumbersome schemas and unnecessarily complicated application code. The document model has limitations. For example, you cannot refer directly to a nested item within a document, but instead you need to say something like the second item in the list of positions for a user 251, much like an access path in the hierarchical model. However, as long as documents are not too deeply nested, that is not usually a problem. The poor support for joins in document databases may or may not be a problem depending on the application. For example, many-to-many relationships may never be needed in an analytics application that uses a document database to record which events occurred at which time. However, if your application does use many-to-many relationships, the document model becomes less appealing. It's possible to reduce the need for joins by denormalizing, but then the application code needs to do additional work to keep the denormalized data consistent. Joins can be emulated in application code by making multiple requests to the database, but that also moves complexity into the application and is usually slower than a join performed by a specialized code inside the database. In such cases, using a document model can lead to significantly more complex application code and worse performance. It's not possible to say in general which data model leads to simpler application code. It depends on the kinds of relationships that exist between data items. For highly interconnected data, the document model is awkward, the relational model is acceptable, and graph models, C graph-like data models, are the most natural. Schema flexibility in the document model. Most document databases and the JSON support in relational databases do not enforce any schema on the data in documents. XML support in relational databases usually come with optional schema validation. No schema means that arbitrary keys and values can be added to a document, and when reading, clients have no guarantees as to what fields the documents may contain. Document databases are sometimes called schemaless, but that's misleading as the code that reads the data usually assumes some kind of structure, i.e. there's an implicit schema, but it is not enforced by the database. A more accurate term is schema on read. The structure of the data is implicit and only interpreted when the data is read. In contrast with schema on write, the traditional approach of relational databases where the schema is explicit and the database ensures all written data conforms to it. Schema on read is similar to dynamic runtime type checking in programming languages, whereas schema on write is similar to static compile time type checking. Just as the advocates of static and dynamic type checking have big debates about their relative merits, enforcement of schemas in database is contentious topic, and in general there's no right or wrong answer. The difference between the approaches is particularly noticeable in situations where an application wants to change the format of its data. For example, say you are currently storing each user's full name in one field, and you instead want to store the first name and last name separately. In a document database, you would just start writing new documents with the new fields and have the code in the application that handles the case when all documents are read. For example, if user and end user name and end not user first underscore name, inside it, documents written before 8/2013 don't have first underscore name. This is the code user.first underscore name equal user.name.split argument, empty argument, and 0. On the other hand, in a statistically typed database schema, you would typically perform a migration along the lines of alter table users add column first underscore name text semicolon, next line update users set first underscore name equals split underscore part argument name comma for one argument empty comma 1 for the PostgreSQL. Next line update users set first underscore name equal substring underscore index under argument name comma empty string comma 1 for MySQL. Schema changes have a bad reputation of being slow and requiring downtime. This reputation is not entirely deserved. Most relational database systems execute the alter table statement in a few milliseconds. MySQL is a notable exception. It copies the entire table on alter table, which can mean minutes or even hours of downtime when altering a large table. Although various tools exist to work around this limitation, 24, 25, 26. Running the update statement on a large table is likely to be slow on any database, since every row needs to be rewritten. If that is not acceptable, the application can leave first underscore name set to its default of null and fill it in at read time, like it would with a document database. The schema on read approach is advantageous if the item in the collection don't have all the same structure for some reason, i.e. the data is heterogeneous, for example, because there are many different types of objects and it's not practical to put each type of object in its own table. The structure of the data is determined by external system over which you have no control and which may change at any time. In situations like this, a schema may hurt more than it helps, and schemaless documents can be much more natural data model. But in cases where all records are expected to have the same structure, schemas are useful mechanism for documenting and reinforcing that structure. We will discuss schemas in schema evolution in more detail in chapter 4.